In the past videos, we have seen what coroutines are, how to create them, how to launch them, and how to assign them a certain context. We have seen that coroutines use suspend functions to be able to suspend and to give the control of the current thread to another thread when they do suspend. There are many things surrounding coroutines, and we have just seen just a glimpse of them. We started out here in this video where we have seen basic things about coroutines. I explained them in the board, and then we moved on to another video where we learned more about coroutines. Especially we learned about suspend functions, and we went a little bit over the coroutine dispatchers and coroutine contexts. But there's so much to learn yet. We still need to discuss scopes, we need to discuss context in detail, and we also want to talk about other coroutine builders like, for example, async. This video is separated in two parts as usual. In the first part we will discuss async and how that differs from launch. In the second part we will discuss more about coroutine contexts, but this time we are going to go full on coroutine contexts. We will see how they work, the way they manage coroutines, the way a coroutine chooses a thread from the different thread pools, how they get a thread assigned, and what does it mean to have different contexts. To start off, I'd like you to think about one important thing. When we are assigning coroutine context and we say that there are different threads in those different contexts, and one context is, for example, more suited to be used in mathematical calculations, and another context is, for example, more suitable to use with input-output operations, and that another, for example, may be more useful to use in main functions, and another one yet that we can use in an unconfined way, and yet others that we can use in Android. What does that even mean? There are different questions here. And we can think about different ways of looking at this. And we have also discussed in other videos different aspects of this. We said at some point, either in this video or this video, something about that it doesn't matter if a coroutine is using a thread or not. What matters is that we can use other threads once the coroutine is suspended. And we also mentioned that a thread runs at exactly the same speed as a coroutine. Because a coroutine is just a primitive, it's just a concurrent primitive running on a thread. And so the speed doesn't mean anything when we talk about speed as a whole, when we compare a coroutine running on a thread or just a thread. And there is no way of running a coroutine on its own. It needs a thread to run. But what does it mean then, the different contexts? Say, for example, you need to make different mathematical calculations. Why shouldn't we use other dispatchers? Why are we saying that we need to use Dispatchers.Default? Why is this important for our mathematical calculations? We could as well use input-output dispatchers. Where is the difference between them? Why is one more important than the other? And why don't we just use unconfined? It's a free dispatcher, right? It will pick any available thread. Why not use that one? And main, why use main even? So there are many questions perhaps, and this video, especially the second part, will discuss that and will shed a light using different examples on where to use these dispatchers. And there will also be a part about Android. So stick around to this video, because now it's time for us to do code in part 1 of this video, where we will learn about async. So let's get into it. If you remember our first example from the first video, we were looking at the coroutine job class. We made this and we created here one example where we would use launch to launch our coroutines. But now we want to compare these to async. So for that, let's create an entire new Kotlin file. And in that file, we are not going to create a class, but instead we will create an object. So let's do that. Let's go over here and let's just create a new class. And here, let's just name it, instead of coroutine job, let's name it coroutine async comparison job. And let's say that it is an object. And let's see what we get. There, we got an object named Coroutine async comparison job. Here, let's first now create our main method, or in this case, main function. And we can say, okay, let's start coroutine job. It's important for us. And remember that here we should, well, just to keep in line with all the other examples, let's just initialize this with an empty array if we don't give it in as an input argument. And then let's put here a run blocking. As we have seen before, this is important to start one coroutine. And let's just leave it by default. And you already know what default is in terms of context for the Kotlin coroutines. It's the blocking event loop. So with the blocking event loop, we will make these examples and see where the difference could be between launch and async. Now, the main difference between the two of them is, of course, that we can use launch to launch our coroutines. We don't have to wait for the result. And with async, we can wait for the result. And that is important because if we are launching many things at the same time and we want all of the results of those launches, then it's important that we use async. But both of them actually return an object that we can wait upon. And that's what we are going to see in this example. And we are going to put all of these examples in this run blocking body. Let's start with a few things. First, we will make a small example with launch as we have done before. So let's say launch. Let's just say, let's not use any dispatcher as a default, and let's just launch something. Well, let's say started coroutine job, and here let's put coroutine job 1, for example. And again, here we'll use the typical suspend function for these examples, the delay, and let's say that will be delayed for 2 seconds. Then, let me just correct one important aspect of this. We have seen before that we do need that the main function returns a unit. As we get over here, let's create another coroutine. And you should now, at this point, if you have seen the 2 videos before this one, you should now be able to understand that when we'll do this launch, the amount of time that the first block will take to run should be the longest time of the longest running coroutine. So for example, if I say start coroutine job 2 over here, and then I delay for 5 seconds, the total amount this will take to run is 5 seconds. And it's also important for us to see when the coroutine ends. So just as we did before, we're going to say that the coroutine has finished its job at a certain point in time so that we can monitor this. Furthermore, we should also put here the current thread, and we should also put here the current context, which should now be current context. And it's great that IntelliJ does this automatically for us. So we can then just go over at this point at the end and then just copy this. All right, so we've got a clear-cut first example, but this example would run normally just like the first one, so we still don't have any difference here. The point here is that these 2 things that we have done here, they are actually called jobs. So if we make variables out of them, we will find that this is job 1. Let's call it job 1. And then here, let's just call this job 2. So now we've got job 1 and job 2 running. Because this is a run blocking, it will wait for job 1 and job 2 to run. But after this example, we want to run the async example. We still want to make that example with async. For that example to be able to run, we need to make sure that these 2 are complete. And to allow completion of these 2 coroutines, what we do here is job1.join and job2.join. What happens now is that job 1 and job 2 will run in parallel, and when we do a job1.join, it will wait for job 1 to finish, and then it will check if job 2 is running, and then it will wait for job 2 to finish. This is pretty much the same as doing join in threads. It will wait for the thread running for job 1 to finish its task, and it will wait for thread running on job 2 to finish its task. Therefore, the total runtime at this point, it shouldn't be any mystery, it should be just 5 seconds. And just to be sure of that, let's just do a measurement of that, and let's just measure time in mils for the whole block. And in this case, let's just say run, and let's just print finish job. Now this one was wrong from IntelliJ. Wasn't the best. So finished example, finished, let's call it launch example in whatever milliseconds. All right. So now we know how many milliseconds it took to run the first example. It's time now to create our async example. And for that, let's just copy paste the whole thing, because it's just easier to change launch with async. So let's just do that here and then copy this. Now we've got measure time in mils with another body in another scope that will now run another job 1 and another job 2. But we have mentioned before that this will be async operations. And then let's use async for the job 2 as well. What is interesting now is that job 1 and job 2 don't make much sense anymore. We can still join them, which is a strange concept, but we can still join these jobs and we can still wait for them to finish in this way. However, these are asyncs. And if you go up and we try to do a typical thing that we can only do with async, do here await, this will not do anything. If you don't know what await is, you will know right now what it is. If we go over here, we can join, we can wait for the coroutine to finish off this way, but we can also do this, await. And we can wait for it to finish. So where's the catch? What's the difference? The difference is that if we do here an await with join, what we get is a unit. There's nothing being returned with join. It's just a suspend function that returns nothing. So that means that even if we try to put this into variables, just the join, if we just select this and just put this into a variable, it will say that it's not possible even to put it in a variable because it's just a unit. So we cannot get a result from the join method. Could we get a result from the job? Well, if we go here to job 1, for example, job 1, we can check if the coroutine is active, if there's a parent. We can put a listener on join. We can see how many children are there, and we have other things to check if it is cancelled, if it's completed, and we've got a series of not too many helper methods that can help us manage these coroutines more efficiently. However, there's nothing here that tells us how to get the possible return object of these coroutines. So therefore, we launch the coroutines and we have no idea what the return type is. We can check status, that's great. We can check if they are completed or not. We can also do another interesting thing, which is we can cancel it. And we can cancel it from the outside, but we can also cancel it from the inside. So if we go over here and we do cancel, we can also cancel our coroutine from this point onwards. Cancel is something that we will see in the next video, where we will talk about structured concurrency, which is one of the main reasons for using Kotlin coroutines, and it is part of the foundational principles behind it. But we are not having a look at cancel in this video. Instead, we are just comparing launch and async. So we now see that a job doesn't return anything. We can access statuses and we can also cancel them. And this is under many different functions that we can access from the outside of the job and from the inside of the job. And while we're at it, we are talking about job, but job is actually the type that a launch returns. And the job type can be looked at over here. And here we can find the definition of the job type. And we can see here what it is. It is a background job. Conceptually, a job is a cancelable thing with a life cycle that culminates in its completion. A cancelable thing. Jobs can be arranged into parent-child hierarchies, where cancellation of a parent leads to immediate cancellation of all of its children recursively. Failure of a child with an exception other than cancellation exception immediately cancels its parent and consequently all its other children. This behavior can be customized using supervisor job. The most basic instances of a job interface are created like this. So there's a lot to say about a job. And we will talk about all of this in the next video. But that is for the next video. For now, what we want to reach is a basic understanding of the differences between launch and async. Now we are done with job. Let's see what actually happens in async. We are still calling it jobs. Let's see what happens. Now job 1 is no longer a job, it's a deferred. And you can notice already that IntelliJ is telling us that the return type is unit. There's a reason for this, and that is because we are using as a last instruction the print line instruction, which of course returns a unit. We don't see that here because actually it is now returning a print line, and a print line is a void. A void is in Java, and the equivalent to void in Java is a unit in Kotlin, and therefore we get a unit from the print line. And that's why we get a unit here. So the correct way to call these is not actually job, it should be a deferred. Let's call it deferred 1. And now for the second one, let's call it deferred 2. Now we've got two deferreds, deferred 1 and deferred 2. We're calling async. And important to notice, don't be led to think that async is different than launch when it comes to launching them asynchronous. They both run asynchronous. So some of you may be misled or can fall into this trap where you are looking at async and think that that is asynchronous and launch is not asynchronous. They both are asynchronous. It just depends on how we use them. And so if we want to get this object that we return from the async coroutine builders, one thing that will make the example clearer is simply just return something. So let's just simply say that the value that we are returning in this body, it's just coroutine 1 result. And let's say that for the second one, it will be coroutine 2 result. IntelliJ missed the capitalization of the first word. And now we can see that deferred 1 now returns a string, and deferred 2, of course, returns also a string. But we want to have these results back. And when we look now at await now does return a t. That t is our result 1. And in deferred 2, that's our result 2. And our result 1 and our result 2 do have a type. Which type do you think it is? Is it an int, an integer, byte, long, a float? What would it be? Is it a string? It is a string. So if we go over here, we can see that it returns a string, which is the result that we are giving in from this last instruction here. And finally, we can simply just print the result to the console. And let's say, again, not finished coroutine job 1. Let's just say finished async example with results, result 1 and result 2. This completes our example that shows the differences between launch and async. What we could do right now is just simply run the example and see where this takes us. And to run this example, we can just go up here, run it. And before I run this example, I have another question for you. How long roughly do you think this example will take to run? Is it 5 seconds, 10 seconds, 15 seconds, or 20 seconds? But before I do that, I do need to correct one thing. I'm sorry about that, which is over here. This is not the launch example. This is the async example. And before even we start running this, it's important that we do get the complete result of this. And so we also need to do another important thing. If we use apply here, it will be able to run this instruction and still return the amount of time it took to run the whole thing. So let's do it here. This will be the async example in milliseconds, and this will be the launch example in milliseconds. And then finally, we can just say that to run both examples. All right, so now we can run and test our example. And we're now waiting. It took 5 seconds for the first example to run, and then it waits for it to run. And now the second example, the async example, it takes 5 seconds to run. And we can see that we have both results, coroutine 1 result and coroutine 2 result. And we can see that we already get the results of the two coroutines launched with async, the one over here, coroutine 1 result, and coroutine 2 result, leading to a total of about 10,000 milliseconds to run, 10 seconds. So if you guess 10 seconds, then you already have a better understanding of coroutines and how they work. Now, important takeaways from this example. When we use async, we get as a result a deferred, where we can wait using join as well, but we can also get the result. With deferred, there is one thing that is probably important to have a look at, and that is, what can we use it for? We can also cancel, we can join, we can do an on-await event listener, we can get completed, we can also get completion exception or null, we can do other things, and there is a difference between job and async. But the primary difference is, simply put, that we can get results out of async and we cannot get the results out of a job, meaning if we run with launch. So async is quite different than launch. We can both run them in parallel, they can both run concurrently. There doesn't seem to be much of a difference between them. But what I want you to take away from this example, from this part of the video, is that the main difference is just that at this point. There are important differences to understand when we talk about structured concurrency, but that is something for the next video, of course, as I've mentioned. And to best visualize these examples, the one we saw over here with launch, and then going forward to the async examples, is to see this in our charts. As we have done in the previous two videos, we are now going to the charts and see how this works with that visualization in mind. So if we go over here to our chart, now it's empty. We first need to draw our lines. So let's draw our axis here. For example, over here, let's just draw a straight line here. This will be our time axis. Let's just say milliseconds. The unit doesn't really matter. And then here, we will just draw another axis where we will represent our threads, where our coroutines will run. So if we draw another line over here, and then make it continuously up until around here, and say that this is the line of our worker thread, then we will be able to represent here our coroutines. And so if you remember, the coroutine context for this coroutine is the blocking event loop, right? And so let's just remind ourselves that there is a blocking event loop here. And the reason for that is that we need to understand that for this example, we are still running one single thread. Because what we want to understand is the difference between launch and async, and how does that differ when we represent it in a graph. And so the first thing we do is represent the first coroutine that we create with run blocking. So let's give it this color, and let's say that it will run up until this point where it will launch the first coroutine with launch. And then let's say that this coroutine, the launch coroutine, takes some time to run until it reaches a delay. And then after that, the thread gets released, and then it will run the second launch until it reaches delay. And then finally, the thread created with run blocking will continue to run up until we've got the two joins that we have seen before in the code. And it will stay here waiting for all of these to complete. Because there's waiting from this point onwards, from this green point onwards, there is nothing running and the thread is available. It's waiting for the two different coroutines to run. And so it blocks here, but it will wait on that thread in this blocking event loop for these two coroutines. So nothing else will run on that thread. So important to notice is that here we do a wait of about 2 seconds. So let me just put here another line, and let's say that this is 2 seconds. And let's say that for the other coroutine, we've got then about 5 seconds. Let's say that this is 5 seconds. So we've got 5 seconds. This amount from here to here is negligible. And so the total amount of time that this takes to run is, of course, around 5 seconds. And that is up until here. Now, the run blocking coroutine is actually blocking this thread. And so this thing over here, let's put it the right color, over here all the way up until this point, and a bit further, it's blocking the thread that is part of the blocking event loop context for this coroutine. And then from here onwards, the second example will run. And this example is the example of async, which, I guess from this graph, you can see exactly what will happen, right? So there will be another coroutine where we will launch with the first async. And it's the same thing. It will start running until there's a delay. And then there will be the fourth coroutine with the second async. And the second async will then run something up until it reaches the point where it calls the delay. And so the first one will wait, of course, 2 seconds. Let me just put it here like this. And let's say that it's waiting right about here, 2 seconds. This isn't perfect. I'm doing my best with this piece of paper. And then we can then say that the other coroutine will run from this point onwards. And that could be over here. And let's say that it will run for about 5 seconds. So that we get a better visualization, let me just put here 5 seconds so that we can see this better because the contrast isn't that great. And so we've got here a total of just about, let me just put this correctly, about 10 seconds. So that was our 10,000 milliseconds. But as we can see, there is no difference when we run async and launch. When we use launch, we've used join to wait for them. Here, we've used the await to get the result back from our coroutines. What we also see as a similarity is that the run blocking coroutine, the one we created with run blocking, will continue from this point onwards, and it will block up until the second coroutine is done. Well, in this case, until the last coroutine is done, because here at this point is where the await returns back for the first coroutine, and then a little bit more further, the await for the second coroutine. After the run blocking, we release the run blocking code block, and there's a tiny bit of code that runs, which is part of the main function. And so this is a map, if you will, of how we can visualize this example in our minds about how it works. The difference between the two different examples is that here we've waited with join and then join at this point and at this point, and here we've waited with await at this point and at this point. This one returned a string, and this one was the unit. Yes, because it's a join. So this is the example of how can we visualize these two different launch examples. One where we wait with a join, where we don't get the result back, and the second one where we get the result back with await. And in both of them, we are waiting for the two coroutines to run, and in both of them, we are blocking while we are doing that process. Important to note is that this we did with job. So in this example, we've worked with a job. In this example, we've worked with a deferred. So this is a deferred. This is the launch example. And this is the async example. All right, so this is how we can visualize this and understand how this example works. Now we will move on to the second part. So let's go there. So now it's time for us to understand how this operates, these basic principles, in coroutine contexts. Because here is where we will see major differences, and we will try to understand what are they for, these contexts, and how come there are differences between them, and if they all run in threads, why do we need to make a difference between the thread pools that they can pick from, and what makes one more efficient than the other for this or that case. So let's now start the part 2 of this video, which is called Coroutine Contexts. So let's get into it. We already know that there are 4 different dispatchers that we can use in our Kotlin coroutines. We can choose between Dispatchers.io, Dispatchers.Default, Main, and of course Unconfined. And we are going to see all of those in detail now. And I have this example already prepared so that we can test the Dispatchers.Default context. But before we run these examples, we need to have some sort of tool that allows us to see the details of our JVM when we are running these coroutines. We want to see exactly how many threads are being created and how this plays out when launching more coroutines than the ones that are expected to run with Dispatchers.Default. What happens when we exceed our CPU cores? So our tool, if you guessed Visual VM, then you got it. That's what we want to use. But I need to tell you, especially if you are someone who don't have this installed in your computer, how to install this, but only for my favorite operating system, Linux, because the video isn't about how to install Visual VM, but I just want to shortly tell you how to install this in a Linux machine. And for that, we can go here to the command line. And over here, we can just simply run a sudo install command. We could do that, but I also can show you that I have a makefile over here that installs all of the necessary commands for this particular project. So this is E03 Kotlin test drives on GitHub. Make sure to check the description for the location of this project. But I have here a command called install Linux, this one over here, where it installs all of this stuff, JQ, curl if you don't have it, Visual VM here, and then it also checks the current version of Gradle. This is probably not important for us in this video. This is what's important for us, Visual VM. If we go to the command line, now of course I already have this installed locally, but if we just run this command sudo apt install visual VM, it will probably now just say that I have him already installed, so nothing much happens. But this means that if you do that in your machine and you do not have the Visual VM utility installed, then this can be a way. There are many ways also to run it. We can use it via IntelliJ with the Visual VM plugin. However, I find that sometimes not the best tool to use, so I prefer to use it directly from the command line, but you do it as you will. There is a plugin for that, I can show you. I also have it installed on my machine, but if we go here to plugins, we can see one particular plugin, and this is this one. Visual VM Launcher by Wojtek Grasa. I hope I'm pronouncing that correctly, I'm not sure, but this is one plugin that you can use to connect your Visual VM Launcher with your IDE. It can be useful, but I use it from the command line. Anyways, this is the next example we are looking at. And the reason why I have this example here is that we understand the limitations of Dispatchers.Default. We have mentioned before that Dispatchers.Default are specifically made for CPU-bound operations, which most of the time mean operations that require a lot of math. These operations don't necessarily need to have suspend functions. The algorithms may or may not run suspend functions. The threads that they run on are optimized to run with these kind of operations. And one of the reasons why it is limited to the number of cores of our machine has to do with the fact, first of all, it won't be able to do much more with CPU-bound operations. If there are more threads, they will be blocked anyways because they are physically limited to the CPU usage. And on the other hand, we want to prevent thread exhaustion, and that means we don't want to spread the calculation to other threads that are potentially useful for other kind of situations, such as the input-output dispatcher created coroutines that are running on that context that is specific for input-output operations, which is something that we will see in the next example. But for now, let's just start running this example and see what goes on in the virtual machine. So let's start our application. But before we do that, let's first go through the different parts of this code. The first part here is it calculates the number of available processors. This machine has 8 cores. So that means that here we will get 8 cores, and then it will launch 8 times 2, 16 coroutines at this point over here with launch. And it will launch all of them with this context Dispatchers.Default. And then in the body of the coroutine function, we will see that it will print out the running thread, and then it will enter an endless loop to calculate the square root of random numbers. So let me just ask you first, what do you think will happen when we run this code? Do you think that the code will be endlessly running, or do you think that this will run very quickly, or do you think that we will have lots and lots of different coroutines running? Let's see what happens according to what I have explained about the default dispatchers in Kotlin Coroutines. Let's just run it. And we see now that the code is running, but it doesn't seem to be doing anything. It has not stopped yet. And it basically runs 8 coroutines that have taken over 8 different threads. These are 8 threads from the thread pool of the default dispatchers. We've got 8. This matches our expectation from the default dispatcher. So if you answered and if you thought that the coroutines would be blocked, that is true, they are blocked, and there are 8 of them at the moment running. We can see this also better in Visual VM. In our command line, if we run Visual VM, then we should see here somewhere the different processes that are running that are Java based. And the one that we are interested in is the one that we have running on our IntelliJ, and that is this one over here. And if we maximize this and have a look at the number of threads that are running, we can see that there are 8 threads. So it's not a question of our code. Our code is running fine. We've got a log of 8 different threads, And these different threads we can see over here, they are in green and they just keep on running. There are even no more threads being launched and there are no more coroutines being created. It's just stuck there on that loop. That means that at this point over here in the repeat, nothing more is happening. It's got to 8 coroutines and the code is stuck here on the loop. From here, we can conclude that we are running our coroutines with a limit of the number of threads equal to the number of cores that we have in our machine. That is, in this case, 8 threads. We've got 8 threads in our thread pool. But is this the only thing that the default dispatchers provide? I mean, saying that the default dispatchers are important because they perform mathematical operations and that they perhaps don't launch a lot of threads, that could be a justification to separate input-output dispatchers and default dispatchers, but on its own doesn't sound like a strong reason to make a distinction between default dispatchers and input-output dispatchers, or the other two that we will see later on in this video. There is one example over here in our code that is called load coroutines work steal example. I've got here another runnable that will launch different coroutines. Again, the same kind of example where we double the number of coroutines in relation to the number of cores that are available in our machine, and then we keep launching these different coroutines. But we do have this delay over here, and this delay separates the upper part of our coroutine body from the lower part of our coroutine body. The upper part makes a calculation of the duration that we need to wait per coroutine. We've got here delay for that duration, and that duration is calculated by checking out the index of the coroutine that we are launching. If the index is an even number, then that coroutine will wait 1 second, and if not, if it is an odd number, it will wait for half a second. And the idea here is to create an imbalance between odd and even numbers of the different coroutines and make sure that it will all run in about 1 second. The idea is for us to see the effects of using the default dispatchers in this specific case. This is not a case where we are just using mathematical operations. A delay is not a mathematical operation, but this is just for illustration purposes. What I want us to get from here is how the coroutines are going to use different threads. Here they will use one thread in these 2 lines, and here they might use the same thread, but odds are that they will not use the same one. Let's run the code and see what happens. We see now in the logs that we've got different worker threads, and every single thread has run under a coroutine. Coroutine 0, for example, ran over the default dispatcher worker 1 thread. And we can now have a look at which one of these coroutines have used this thread. And we can see already that coroutine 0 has used it, coroutine 10, coroutine 12. And if we go further down, we can see coroutine 14 has used it as well, just at the beginning. And that's it. For this one, only the upper part of the coroutine bodies of the different coroutines, 14, 12, 10, and 0, have used this thread. Let's try, for example, default dispatcher worker 2. Where has this been used? For this one, coroutine 1, 5, and it has been used to finish off coroutine 4 and coroutine 10 as well. And so we can see a different distribution. What we don't see is more than 8 threads. We see only 8 threads as a maximum at this point. Remember that we launched a double number of threads in relation to the number of cores available on this machine. So this makes sense. Doesn't sound like anything different. But what's important here to understand is that it didn't went above the number 8. It didn't went above the number of cores. And there is a reason for that. When we are launching different operations that are using mathematical operations, that are doing computations that are considered heavy computations, these would occupy the CPU anyways. And that would mean that we wouldn't want to create more threads than the number of cores. And the reason for that is that they would be blocked anyways. if we would have started this program with the dispatchers IO, it would have created more threads than the ones that we need. And I want you to pay attention now to the amount of time it took to run this operation. Because they are, in a way, evenly distributed between coroutines that take 500 milliseconds and 1 second, they were able to run in between them. And that means that the result is about 1 second. That explains this result. If I run this with IO, I want you to observe what happens now if I run with IO. Running this with the context that is meant to be used for input-output operations will result in how long do you think? Exactly the same time, about 1 second. But look at what just happened to the different threads that are running. We can see that it has generated almost the double of threads. Instead of generating only 8 threads, it generated, I believe now, 17 threads. It generated 17 threads, which is more than what we need for mathematical operations. And the reason in this case why it takes exactly the same time, it's purely because of delay. But again, delay is difficult to incorporate in an example of a default dispatcher because it's meant for mathematical operations. However, heavy mathematical operations are difficult to simulate in small examples like this. And therefore, this is kind of the best we can do with delay to play around and understand the big difference between one and the other. So I just want you to get the idea that the default dispatcher should be used for mathematical operations, that a delay isn't something that should be a part of that process, only for this case, for illustration purposes, and that the main reason why this dispatcher has been made specifically for this is that generating more threads wouldn't make sense because these are CPU-bound operations, which is part of the reason why we use default dispatchers. But before I go into this, you may have noticed that the example that we just saw is called work steal example. And this is something for Dispatchers.io that I really want you to understand. The concept that we have just seen, where we start in a thread and then we call a suspend operation, that if it suspends will mean that when the coroutine regains control of a thread, it might be another one and very likely be a different one. That is something that is being called in the community as work steal, as some kind of phenomenon that is called work steal. Work steal, I've tried to look for it. It is not an official part of the Kotlin documentation. It's being used everywhere. You will find it everywhere. But it is not an official part of the Kotlin Lang documentation. Instead, we should refer to this as an even distribution of coroutines in a thread pool. Words are important. Words are important. Semantics are important. Sometimes we think, what's in a word? There's a lot in a word. It can mean a lot. If we say work steal, we better know what that means, because if it's not used in the documentation, there might be a reason for it. Now, using input-output dispatchers is a different story. Input-output dispatchers are not limited to the number of CPUs. They are, in fact, not limited at all. And you may have heard about this limitation of 64 threads. It only means that it's the initial pool size of that pool of threads for that specific context. It will grow as it's needed, and it will also shrink as it's needed. But it is something that we cannot observe in the code directly. We can make experiments, and we will do one right now, but it is something that we won't be able to see the effects on running the code. What we need to bear in mind is that Dispatchers.io rely on the simple principle that if you need more threads, it will make sure that you will get more threads if it's possible to make them in your JVM and with your current physical resources of your machine. So the idea is really to use it for heavy load operations, not heavy mathematical operations, heavy load operations, like for example, making REST requests, reading, writing files, anywhere where we have that small amount of time that we need to wait to get a response, like for example, a socket, like for example, WebSockets, like for example, any kind of communication where we open a stream and we need to wait for anything that is coming down the stream, or we need to send something up the stream. Those are things where the Dispatchers IO might help you. So let's look at one example of that right now. I have it just next to this one. Let me just revert this change. And now let's go to the next example, which is this one over here. This is an example that will launch different coroutines with the input-output dispatchers, and it will simply run this read text on a file, and then it will print out stuff to the console that we will interpret. This will run different coroutines as we have seen before, and these coroutines will log different things in the console. Namely, they will log how many threads are active at a certain point in time. The idea of this example was specifically to try and find out when the thread pool of the Dispatchers IO context would grow. It's not that easy, and we will see with this example why that's not. So, what are we actually doing with this example? Let me explain. If we run test, which is this function over here, we are passing in an argument that is an integer, and this integer represents the number of coroutines that we want to launch with the input-output dispatchers. If we go now inside run test, we will see exactly what it does. It will print out a line which will separate every single test from each other, and then it will launch all of the different coroutines under the Dispatchers IO, and there it will read a file which will be written at the beginning of the program right over here, and it will write it to example.txt, and it will just write a text Kotlin Coroutines Dispatchers IO, which is a reference to the example, of course. And the important thing also is that it will sleep for 10 milliseconds, and then it will print the active running threads, and then finally it will print out the amount of time it took to run. An important distinction here is that I am purposely using sleep here because I want to force this to generate multiple threads. We already know that with coroutines, whichever they are, if they suspend and come back, the likelihood that another thread will be used instead of the first one is very high. So this really happens in coroutine dispatchers. The difference here is that we want to see how this is going to evolve, and to force the creation of new threads, we are actually going to sleep 10 milliseconds and make sure that the input-output dispatchers will just keep on creating new threads. Let's see what happens and how long this takes for every single moment. If we run this example now from this point onwards, let's see what we get in the console. It has just completed, and we see that in the first example we are launching 10 coroutines and we have achieved 17 active threads at one given time, and we see that it took 28 milliseconds to complete. Then when we launch 50 coroutines, we see that 55 threads have been launched and the whole thing took 19 milliseconds to complete. Then we launched 100 coroutines. 71 threads were traced. So we've got 71 active threads. At this moment in time, we also should think of the 64 threads as an example. And it's important to understand that limitation. If our machine has under 64 cores, that means that the initial thread pool has 64 threads ready for us to use. if our machine has more cores, then we will be able to use in the initial thread pool those whatever amount of threads are equal to the amount of cores. Now, if you have a computer with 64 cores, that's great. I think that would be a very efficient computer in current times. But yeah, 64 cores, 65, 66 cores. If you have more cores than 64 cores, then that is the leading number that will define the pool size for input-output dispatchers. But normally you really will get 64 threads in the beginning. It's not technically a limitation of the number of threads, it's a limitation of the initial pool of threads when we start running coroutines under the Dispatchers.io coroutine context. So here we probably cross that line. And so on, it goes further up until 10,000 coroutines. This one over here. And in the last example, it took about 1.5 seconds to complete. And we detected 114 active threads. The idea of making this test is also to see if, when crossing that threshold, if anything would be slowed down. Because the idea is that this pool will upscale with the need for more threads, which has occurred here, but that is because we know it. Theoretically, that's what it does. Let's try and see if we eventually see a difference if we make a graph out of these results. If I pick up the data that we've got over here, I can just pick up the first one. So we've got 10 coroutines. We've seen that the amount of time it took to complete 17 threads took 28 milliseconds to complete. Okay, so this is our raw data so that we can plot a chart. The chart we want to plot consists on the number of threads as the x-axis and the time it took to run as the y-axis. So if we select this n, and then we select milliseconds, and then we plot an xy chart, then we will see something curious about this. Let's see if this one is the one we want. Yeah. We see a straight line. And this is important. Why is this important? It's because here we can see that the thread pool, the upscaling from the thread pool, doesn't really influence the time. It doesn't really influence the performance. It may do for very, very heavy processes, but in most cases this would be negligible. The upscaling of the thread pool, it's something also that is more designed for peaks of usage. So if you've got lots of requests coming in at a certain specific time, or because something special is happening with your application in a certain feature that you are providing to your clients, then it's important to note that the performance will probably not be hugely impacted because of the upscaling of the pool size. It may be impacted by other things, but the initial pool size of 64 threads might not represent a huge difference in practice. The idea of the input-output dispatchers is, in the end, simply put, if we need to launch a lot of coroutines and those do not involve CPU, and those do not involve huge amounts of heavy CPU-bound operations, then we are probably good with Dispatchers.io. But it's important also to know that Dispatchers.io can be used also with CPU-bound operations just as long as it justifies mixing them with input-output dependent operations. And so Dispatchers.io and default dispatchers end up being the most important kind of dispatchers that we want to use in applications, especially server-side applications. We do have two more dispatchers to look at, and one of them, the next one, is probably used more often than you think. This is a dispatcher that appears also using Spring applications, using server-side applications. It is called the unconfined dispatcher. And I, of course, have an example of the unconfined dispatcher, which we can find in this example over here, loading coroutines unconfined. The important difference between the Dispatchers.Default and the Dispatchers.io when it comes to the unconfined dispatcher is that the unconfined dispatcher will start a coroutine with the same thread that called the coroutine builder that created it. If we look at our example, we will see that we start here our code with run blocking. Here we have the body of the run blocking section, and then here we are printing out the current thread in that run blocking. As we know from before, this will be the main thread, which will have the blocking event loop. But when we launch with unconfined, it will have a different context, not the blocking event loop, but it will have the same thread at the start of the coroutine. So the first set of instructions before the first suspend, before the function actually suspends, will have that same thread. That means that when these two coroutines are launched, this one and this one, they do start in parallel, but here and here, they will share the same thread, which means that they will run concurrently. Up until this point for the first coroutine and this point for the second coroutine. From this point onwards, there's also another suspend point for both of them, but they will take another thread, most likely. And so the idea of unconfined is more for specific cases where would this make sense. Most of the times, it's not really something that we want to use. We will explore the usages of this particular context in other videos, but for this video, what's important is that we understand that unconfined doesn't really care what kind of thread it uses. It will pick a thread from a random place, a random pool. It doesn't matter. It needs to find the first available thread. And that also means that it is slightly unpredictable. It is used for things like testing, but also in frameworks. As I mentioned before, the Spring framework apparently uses it. If we test it with some code and we try to log in things and try to find out what the current coroutine context is, very likely we will find the unconfined dispatcher. It doesn't mean that this will happen for all versions of Spring, but there is probably a reason for it. One advantage could be the simple fact that it keeps the thread. But more on that after this small demo. We will now run this program and see what we get in the logs. Let's just wait for it. I had run it before with a different version, but now we have the result and we can see that it starts the two different coroutines right about at the same time. It starts the first one and then the second until it finds a suspend point. And after that suspend point, we see that it changes the thread. Instead of using the thread main, it uses this one, the default executor. And it also changes the context to Dispatchers.Unconfined. We also see something different here, that we start with blocking event loop as the context in run blocking, and here we have the new Dispatchers.Unconfined context. But unconfined is something that comes with the framework. It is not really advised to use it explicitly in our code. It is there for specific cases, maybe if we want to implement a test framework or just a framework, but Dispatchers.Unconfined isn't really suitable if we want to make our own library or if we want to implement our own services. There are specific cases for it. And it is important to understand for every specific case what could be the benefits of using the unconfined dispatchers and what could be its pitfalls. A big pitfall of unconfined dispatchers is simply that they are not predictable, that we cannot predict what kind of thread they are using and which kind of pool they are taking the thread from, so that the coroutines can run on them. But for the rest, it works just in the same way as we have seen before in the first and the second videos. They have the same functionality as any coroutine dispatchers, and that means that coroutines created with this dispatcher will also work in the same way. These three dispatchers are important because they work with different threads and they allow the coroutines to be spread out through different threads. They have different ways of working with them. Default dispatchers are limited by the CPU, are specific for CPU-bound operations. Dispatchers.io, they can upscale the thread pool or they can shrink the thread pool, and coroutines created with unconfined dispatchers will keep the thread that created the coroutine itself. They will keep using that thread up until the first suspension point in their runtime, but they will then pick random threads. The last coroutine context that we need to look at is the main coroutine context. Now, main is very different and very strange because main is used for things like the UI, what we call the graphic user interface. And the graphic user interface, if you are used to dealing with applications that use that, you know that there is one thread responsible for the whole thing. It is responsible for rendering, for getting data from the different controls in the UI, from getting data from the data fields, for using the buttons to trigger events. And this means that it can be used only things like Swing, like JavaFX, and of course, Android. And we are having a look at an example on how to use the main dispatcher with a Swing application, which curiously enough is probably the way that Visual VM was built. Judging from the look and feel, it is probably a Swing application. So let's see where that example is located. The example of the Swing application is located in the project right over in the Coroutines module, and it is one submodule, and it is called Coroutines Swing. And here we can have a look at the bit of code that will start everything. Our application is a Swing application. The Swing application needs Swing libraries in order to be able to run. But we are using coroutines with it. And with those coroutines, we are using the context of Dispatchers.Main. That is the main dispatchers. What we are doing with this Swing application is simply launch a JFrame, and then we just put a label, a button, and then we add an action listener that will start a coroutine with the main dispatcher, and then we'll put on the label running task, and then after 3 seconds it will put out on that label task completed. It will then format the frame and simply show us the frame in our program. Before I run this, I want you to see one important thing about running with the main dispatcher. The main dispatcher context can only be run on applications that implement a main dispatcher. And a main dispatcher is something different than a main scope. We will talk about scopes in the next video when we talk about structural concurrency. But for now, we are looking only at the main dispatchers. So it's important that we know that distinction, that there is a main scope and a main dispatcher, and not mix both terms, because they are very similar and we can confuse them. If we go to the dependencies of this project in the POM file, we will find that there are a lot of dependencies that are important to run this project. One of them is the Kotlin X Coroutines Core JVM. This is important so that we can have coroutines in our application, but we have also the Kotlin X Coroutines Swing. This is the library that provides us with an implementation of the main dispatcher. If we remove this one over here, or we simply just comment it out, and we then update Maven, we should be able to now run our application with a small defect. And we will see that error right now. If we run it from here, we now have got our frame. Then we need to press this button to start our task. And this will be kick-started at this point over here. This body of the add action listener will start and will make some changes to our JFrame as we have seen before. So if we start it now, we will see immediately that there is an exception. And this exception will tell us that the main dispatcher is not available. It says specifically that module with the main dispatcher is missing, add dependency providing the main dispatcher, example given, Kotlin X Coroutines Android, and ensure it has the same version as Kotlin X Coroutines Core. It's important to keep the version because we want to make sure that our application is uniform and that we don't get unexpected errors by using different versions. So if we add this library again, where then our main dispatcher is implemented, we should now see that when we start the task, it runs the task, and then finally, after 3 seconds, the task is completed. Now, the main dispatcher is something important for structured concurrency, but it's very important for Android applications. I don't know about Swing. It's definitely important for Swing applications. We have seen that with the Visual VM. It is an application implemented with Swing. Other applications are also implemented with Swing. We can even make our own that is implemented with Swing, and that we need to pay attention to use the main dispatcher. The same thing is valid for Android applications. But that is something for the next video. This was a short introduction to the main dispatcher, because the main dispatcher is something very interesting that can be used in different kind of ways. It can also be used in JavaFX. It can be used in Swing. It can be used in Android and any kind of framework that implements the main dispatcher. All right, so we have reached the end of this video. We have gone through different aspects of launching coroutines. We have learned what async is and the difference between async and launch. We have seen the 4 different dispatchers that are important to create coroutine contexts. We didn't went into details about transformations to the coroutine context. That's something that we will learn in the future videos of this series. It's also important for us to understand the different usages with Dispatchers.io, Dispatchers.Default, Dispatchers.Unconfined, and Dispatchers.Main. All of these 4 dispatchers are very important for our application, and it is very important that we understand the applications for them. Where can we use them and why? I think with this video, I highlighted those important aspects and how and where these dispatchers should be used. If you have any questions about this video and about the subjects discussed in this video, please leave a comment in the comment section. That is very important for me also to understand perhaps more things that I can add in the next video. It is also important that you read the description, because I will put in the description lots of important things. Among them, one thing that I have not mentioned in this channel, and that is that I do have very old applications from 2013-14 that are Android applications. I've been improving them, and I have been giving a new life to my Google Play account. These applications will be used in future videos also to highlight how to use Android applications with Kotlin Coroutines. I think those will be interesting videos, but it will not be this next video. It will be videos further ahead in weeks to come. So please make sure to check the source code. It's completely free to use, and you can check it out and see if there's anything good about it. I have not improved a lot these applications. 2 of them are already using Jetpack Compose. Please have a look at GitHub, and if you have suggestions about how can I improve those applications, please let me know in the comment section as well. For now, thank you so much for watching this video. I really appreciate that you reached this far watching the video. I did this video with the goal of explaining to you, the viewer, how coroutines work and where can they be applied, of course. And I hope to see you in the next video. And until the next video, stay tech, keep programming, be kind, and have a good one. As a short disclaimer, I'd like to mention that I'm not associated or affiliated with any of the brands eventually shown, displayed, or mentioned in this video.